All right, section 6.4 is called proportional reasoning. And as we take a look at this, we'll do about half of this section today. We first have to talk about ratios. We've mentioned this word before, but ratio notation is written as A, and then you've got a colon B, or A divided by B like a fraction. That's the way we're mostly going to read it, or write it rather. And it's read A to B. It's a comparison is what it really is. There's two different types of ratio comparisons though, and people get tripped up on them quite frequently because they're not considering what they're really comparing. One of them is a part to whole ratio, and the other one is a part to part ratio. And to show you the difference, this example explains it. There's 15 students in a class, 7 of them make an A. The part to whole ratio of A's to the whole class would be 7 to 15. But the part to part ratio of A's compared to non-A's would be 7 to 8. Okay? And we will encounter this part to part, part to whole stuff happening again when we get into our section on probability. And we'll talk about odds and probabilities and odds and how those are related to this particular idea. So this is going to come back up one more time later on. And so it kind of depends on how you're comparing things as to which one you use and in which context. So if, for example, though, we can move back and forth between these. So here, let me go back to the example we just had. Where did the 8 come from? Yeah, it was the 15 minus 7, actually, right, Summer? Yeah, it was 15 minus 7, right? 15 total people, 7 A's, so there's 8 that didn't make A's. So we should be able to move back and forth between these two ratios if we're given the right information to do that. Example 1 is one of those scenarios. If the ratio of boys to girls is 2 to 3, what is the ratio of boys to the whole class? So we're talking boys to girls, and it's 2 to 3. So what would we do if we wanted to do boys compared to the whole class? Yeah, we'd add the ratio components of the boys and girls together. 2 and 3 would be 5. So in some sense, you would actually be able to say then that 2/5 of the class must be boys, right? From that example. We can also go the other direction. If 3/7 of the class are girls, then what is the ratio of boys to girls? So again, if I can sort of identify the correspondence, it makes it easier. This is girls compared to the class, right? 3 to 7. So what would I do to get boys compared to girls? Yeah, and I would get 4. So this would be 4 for boys, but it's not 4 to 7, it'd be 4 to 3. Yeah. So boys 4 compared to girls 3. Look good? Awesome. Okay, so got to have ratios first, and now that we have this idea of ratio down, these comparisons to be able to make, we have proportions. And proportions are simply a statement that 2 ratios are equal. That's all it is. Once we have proportions, it's really nice to have a few facts about them to see that if I set up a proportion and Hannah sets up a proportion, we might set them up differently, both be correct and both get the right answer, and there's reasons why that would happen. So that's coming about by these proportionality theorems. So these proportionality theorems, very useful, tell us that if we have all real numbers and denominators are not 0, that's all the conditions at the beginning. Real numbers, denominators are not 0. Then A over B is equal to C over D, if and only if AD is equal to BC. And you probably have an affectionate name for what that just did, which is what? What'd they do? It's not a reciprocal. No. Cross multiplication. Yeah, cross multiply. Yeah, usually that's how we think about that. So we multiply across this diagonal, and we multiply across this diagonal. So we have AD equals BC. Interestingly enough, we can continue that idea. Again, A over B is equal to C over D. If and only if B over A is equal to D over C. So if you are comparing this piece to this piece, what'd they do? Yeah, both sides, right? And that should make sense. If they were equal in this format and I flipped them both upside down, they should be equal in the other form as well. Okay? They're reciprocals. So the first one is one you're very familiar with because we use it a lot for solving purposes. The second one makes good sense to us because we understand the idea of just flipping these ratios around being the same. The last one, Theorem 622, says, again, A over B is equal to C over D. If and only if A over C is equal to B over D. So on this one, what happened when you compare the two different ratios? How did things change? Okay, so be careful, it's not both numerators, right? Yeah, B and C switched spots, right? Do you see that? The A and the D are in the same spaces as before, but only the B and the D switched. The reality is, we could also have left B and C where they were and switched A and D in a similar argument. But think about what would happen if you cross-multiplied these. You'd get the same thing, right? Yeah. So based on the very first theorem, the last one also has to be true. That when I flip one of the diagonals and change its location, I'll get the same fact that I had before. And what actually happens is it means that you're comparing different quantities or comparing quantities in a different way. And so as we do some examples, I'll show you how you would have ended up with different proportions and why they would both still work. Okay? So we're going to do some examples of proportions. All right, I think we'll attempt to do 3 examples today, and then we'll save the last ones for the next time. All right, Jim. Jim found that after working for 9 months, he had 6 days of vacation time. If he accrues vacation at the same time at the same rate, how many days would he earn in 2 years? So we have to figure out what we're comparing. So what are the things that are being compared in this scenario? Okay, but months of what? Months of working. So the time he spent working, actually, right? It's really a time amount he spent working, and we're comparing that to what? His vacation days that he earns, right? So there's 2 ways to do that. You can either compare those 2 things as a fraction, numerator compared to denominator, or you can compare them as an equation, left side versus right side. And it doesn't matter what you do, but you will get different proportions, much like Theorem 620 became 622. All right, so let's do, I don't know, which one do you want to do first? Do you want to compare it as a numerator denominator first? Will that work? Okay, so if we compare it as a numerator and denominator, this would be the number of months working. And we can compare this to the number of days of vacation. So let's look at the information we're given as it relates to those quantities. So the first piece of information tells you what he has now. How much has he worked now? 9 months. And I would encourage you to use the units inside of at least the initial setup of this to make sure you keep it all in the right places. How many vacation days does he have that are associated with that 9 months? 6. And this proportion, this business where it says at the same rate, tells you that the ratio is the same. That's what it's telling you. has to work if he works there for 2 years. So if he works there for 2 years, we need to know that in months, right? Okay, so be careful. How many months would that be then? 24 months. And what we don't know, we'll call it X, is the number of days of vacation. Let's solve this, and I'll show you the other option of how we could set it up and why it would work, okay? So on this portion of the solving, I probably wouldn't keep writing the units because I just wanted them there to make sure that you see, look, months and months, days and days, right? They match. That allows us to be careful that we didn't like put years in there for our 2 years that he worked or something like that, or that I accidentally flipped the other side of the fraction so that it ended up being his vacation days on the top and his working amounts of months on the bottom, that kind of stuff. So if I cross multiply, this diagonal becomes what? 9x. And this diagonal becomes what? Okay, just a second. That's what I was trying to do. 144, thank you. What would I do then to solve for x? Divide by 9, right. So what is 144 divided by 9? It's 16. 16 what? Days. These are our vacation days, right? So he's getting, essentially, if he's getting 16 days every 2 years, he's getting 8 days off per year. That's what that works out to being, right? 8 days of vacation per year. Okay, let's say instead you set this up as number of months working, and you did it as an equation across the equal sign to the number of vacation days. So if you did that, you're still going to end up with a proportion, but the proportion is going to be comparing the number of months working in one scenario versus the other one. So the number of months working currently is 9 months. The number of months that we're talking about working is 24. The number of vacation days that we currently have is 6 days. And what I'm trying to find out is the X days amount. Right? The amount that we'll associate with the number for 24 months. And if you cross multiply, it'll still work, right? This is the 9x. And on the other diagonal, I have the 144. Okay, so different ways to set them up. They look different. The comparisons you're making are different, but they actually are just two ways of making the same type of comparison. Okay, so you pick and it will work. All right, let's try a scale. So on a city map, a rectangular park has a length of 4 inches. If the actual length of the width of the park are 500 feet and 300 feet respectively, how wide is the park on the map? So what are we comparing? Okay, length and width, feet and inches, but those are just units. What are we, I mean, the feet and inches are units. What's the comparison of quantities? Well, there's a length and a width. There's something else, though, too. Nope, that's the length and width.
Actual park versus the map.
There you go. Real life versus the map. That's really the comparison we're making. There's a length and a width associated, but the comparison is really being made between real life and the map. Does that make sense? So again, it doesn't matter whether you put real life on top, the map on top, or if you do them across the equal sign, just pick, and we'll go with it. So I'm going to do real on top and my map on bottom. I don't even know if that's what I wrote down before. Nope, it's not. So we'll just go from this on this because I wrote it down. Okay, and then when you're comparing it, the other thing that you guys told me, which is true, there's a length and a width issue, right? And that's true. We do need the length and the width issue here too that we will be comparing. So on the map, what do we know? The denominator part. What do we know about on the map? What information are we given?
4 inches.
The what?
The length of 4 inches.
The length of 4 inches. So we have this part right here. Length of 4 inches. So I'm going to be on the length side of the equation, and I'm going to be at 4 inches in the bottom because the map part is on bottom. What about the width on the map?
X.
That's what we don't know. Exactly. So that's what I'm looking for. That's my X inches. Now what about real life? What do we see about real life in this problem? 500 and 300. And this is one of those places now where you have to use sort of like the contextual way that we think about length and width. Which one goes with length? The 500, the longer one, right? Length is the long side, that's how we think about it. So length would be my 500.
We want to convert it to inches.
We don't need to. We just need to make sure that we're using the feet in both locations along the top. And then we need 300 over here. Okay? So we will cross multiply. 500x equals what? All right, this is 1200. And then what? Divide by 500. And I mean, we're talking about a map here. I know that sometimes it can be sort of tricky to decide, do I use decimals or do I use fractions? The reality is that when we're measuring things, truly measuring things, we don't use fractions. It just doesn't make sense. We measure things to decimal points. So a decimal point kind of answers what we're looking for here. What would we get if we divide 1200 by 500? Okay, but 2.4, yeah. 2.4 inches. And that would be the width on the map. Any questions on that one? Okay, we'll do one more for today. Kiera, kind of like Kira's sister Sierra, Kiera and Dora worked for 3.5 and 4.5 hours respectively on a programming project. They were paid $176 total for the project. Because Dora has fairness as one of her strengths, she wants to make sure that each of them are paid according to the amount of time they spent. How much should each one of them earn? So the point being is that they didn't spend the same amount of time, so they shouldn't just divide it by 2, right? So how would we figure that out? So what are the things that we're comparing here? What comparisons do you see? There's 2 comparisons.
Time versus pay.
Okay, the amount of time they spent versus the amount of pay they got. What else do you see?
The 2 girls.
The 2 girls, exactly. So again, one of them is going to be split across the equals sign, and the other one's going to be a numerator versus denominator comparison. Doesn't matter which one's which, you just pick. So somebody tell me, which one do you want to be my numerator denominator comparison? Do you want to be the girls or the pay versus the time spent? Pay, what'd you say? That's not a comparison. Try again for me.
Like the paid on top and then the girls on the bottom.
Okay, I think you mean the paid on top versus the time on bottom.
Oh,
Is that what you mean?
sorry.
Okay.
Yeah.
Okay. So the amount that they were paid on top, and then that would mean that across the equal sign will be the 2 different girls' amounts they spent and all that kind of stuff. So I have, let's see, Kiera was listed first. So Kiera first, and Dora on the right. Okay, so one piece of information is really straightforward. Which one? Is it the pay one, or is it the one about hours? Hours is really straightforward. We know how much Kiera worked. It said that she worked 3.5. And we know how much Dora worked. She worked 4.5.
So do you know, like, they work that because of the order it goes in?
Yeah, respectively means in the same order. So when anybody says the words respectively, that's what they're referring to. You probably have heard that said before in just conversational structure, yeah. Okay. So what are we going to do about the pay part? This one's trickier than the other two we've done. So
Can you add the amount of hours they worked divided by?
okay, so the real answer to your question is yes. I'm going to show you as a separate step what that would look like, because we didn't set this up that way to start with. So what you're asking me to do is to take one girl. I feel like I didn't spell her name right. No, I did. And compare her to the total. And we could do that. And it's actually a really nice way to do the problem. So I could say Kiera worked 3.5 hours. How much did they both work total? I think it's 8. It's 8, right? Okay, 8 hours total. We don't know how much Kiera made. But we do know in total they made 176. So this would be one way to set it up. And you could compare Kiera to the total, or you could compare Dora to the total. It wouldn't matter. The other way to set it up, if you're comparing the girls, ends up being a little messier in terms of algebra. Because we don't know how much Kiera made, and we don't know how much Dora made. But pretend for a moment that Kiera made $100. She didn't. It won't work. But pretend. If Kiera made $100, how much did Dora make? Why? What did you do to get 76? You subtracted it, right? So if Kiera worked X, not worked X, but earned X, how much did Dora earn? Yeah, 176 minus X. Now, why do I say that that's a little trickier? Well, because you've got 2 X's in your problem. That makes the algebra component of this trickier. The other thing is that Dora has a binomial. It's 176 minus X, 2 pieces, that both have to be multiplied when I cross multiply by 3.5, also making it a little bit more cumbersome to work with. Let's finish it just so you can see how it works that way, and then we can compare it to the other one. I feel like that this is the more natural way of comparing them, Kiera to Dora, but the algebra isn't as nice to work with on this one. So it kind of just depends on how you think and see the problem. All right, so if I cross multiply, my first one is going to be 4.5, oops, X. And then when I do this side, I actually have to make sure that I multiply the 3.5 times the 176 and the 3.5 times the negative X. So what is 3.5 times 176? 660? Like that?
No, 617.
Oh, okay. I thought that's what I heard first, and then I doubted myself. 616. And then I would have minus 3.5x. Then what would we do? Add the 3.5x. So what is 4.5x plus 3.5x? 8x. That's that 8x we got on the 8 we got on the other side of the other side of my screen, basically. And then if I divide by 8, what is 616 divided by 8? 77. Okay, so what did I just find? Amount of money who made? Kiera. This is Kiera's pay. Because it asks me how much should each one earn. Well, Kiera should earn 77, so how much should Dora earn? 99, and there you very quickly see exactly why Dora didn't want to split it 50-50, right? She worked more hours. So this is Dora's pay. If you do the problem like we did on the right-hand side, very quickly you'll get the same thing. There's my 8x. And then what's 176 times 3.5? 616. Right? That's the same equation I eventually got to down here. And again, finding out at the end X equals and stopping would mean that we didn't answer the questions because it needed two answers for this one. How much each girls make.